Hello, we are Team 5. We are going to be covering the design and implementation of a RISC-V system on chip for medical IoT applications on FPGA. My name is Jose Caraballo. I'm the team lead. My background is in computer engineering.
My name is Ivan Zeliasser. I am doing computer science.
My name is Edwin de los Santos, and I am an electrical engineer.
I'm Adrian Suarez, and I'm also an electrical engineer. Hello, my name is Adrian Suarez. I'll be going over the project summary, which is like an overview of the whole project. In this project, as we discussed in the introduction, we'll be designing a medical IoT device to record brain data. This brain data will be using to determine the outcome if you have seizures or not, any brain abnormalities in your brain waves, and basically alert you or as well the medical professional, or and as well both as well. That way, medical professionals could send this to research and research the brain waves and determine if there's a solution or not in the future. As well as we'll be collecting the brain signals using EEG sensors. This will be processed through a web server using a FPGA. The server will be integrated with a fast Fourier transform hardware and machine learning algorithms to measure the data for the abnormalities, of course.
So this is our proposed solution that we intend to implement. In basic sense, a user will wear a smart EEG headset that will streamline the data from a field programmable gate array for signal processing. The system will extract brainwaves features, and these brainwaves will consist of alpha, beta, delta, gamma, and theta uh, signals that will use a support vector machine and send the results to a mobile app. Once it's in the mobile app, this data will be accessible to anyone that's relevant, such as healthcare providers, and will they will be able to do analytics in real time for clinical intervention.
For this section of the presentation, I'll be going over the system overview of the full system block diagram. The diagram that's shown goes over three major subsystems for the brain data medical Internet of Things device. These three subsystems consist of a mobile application, gateway/server, and wearable device. When we start looking at the wearable device will start with collecting EEG sensor data. It will then go into our signal capture and conditioning subsystem, which all that data is being fed into our external analog to digital converter and will then send digitized data to the microcontroller. Following the wearable device will be the gateway/server, where it will collect all that signal data and go through a signal data processing subsystem where all that data will be processed through a butterfly operation module within the FPGA. That's data will follow through into a machine learning module where it can be further classified. And once classified, that data will be stored within the server's SQL database. Once stored, we can start following the communications between the mobile application and the server, where the mobile application will provide that data through a dashboard. It will also provide a user authorization screen, be in charge of the communication systems, and also have basic encryption.
Hello, my name is Ivan Zeliasser, and I'll be going over the activity diagram. The overall objective of our activity diagram is to show and display a robust system amongst all the devices within our network. So the first device overall that we have is the medical IoT device, which is the EEG sensor. It should be able to connect with a mobile app application, and the mobile application is going to check over and see if the user already has an account signed up using Firebase. If it is successful, then we go to the sensor calibration. If it doesn't exist, then the user can create a new account. So when we go to the sensor calibration, we're going to check if the sensors are calibrated. If it goes and it's successful, we go to the next state, which is the idle state. If it fails when it comes to calibrating the sensors, we go back to calibrating the sensors again. After the idle state, we go into data collection. Uh, Data collection, we're going to collect the data from the medical IoT device and send it over to our FPGA server, where it will then be processed and stored. Later on, after that, we're going to have the mobile application request information from the FPGA web server to display it for users' consumption so they can see what their brain activity at the current moment is. And then later on, they can continue to keep on grabbing data, or we can continuously collect data, or we can just turn off the device and have the device just not collect data at all.
For subsystem design and implementation, we will be covering my part of the project, which is signal processing and machine learning. Starting off with the project, I'll be focusing on designing a fast Fourier transform through hardware on the FPGA of the Beagle 5 Fire. The reason for this is because we can allow for hardware acceleration so we can offload any additional workflows that the CPU might have to process for the project, ensuring that we can focus on trying to develop a real-time system. The FFT module will be written in Verilog through the Beagle 5 Fire. Additionally, I'll be training a support vector machine model to detect seizure risks based off of the signal data that was collected through the EEG's sensor network. Like mentioned before, we'll be collecting alpha, beta, delta, theta, and gamma brain signals. Additionally, I'll use MATLAB to test and compare the fast Fourier transform and support vector machine results. The way that I'll be doing this is by using CSV data from the ESP32, introducing that as an input for the fast Fourier transform that I'll be designing on MATLAB. Off of those results, I'll be sending that to the trained SVM I will also contain in MATLAB as well. This provides a predictive model of what the subsystem of what the medical IoT system should be providing when it displays results to its users. This will be vital in both ways for testing the system as well as providing insight on how the system should be behaving. Finally, the data that's been classified by the SVM should be sent to the mobile application to display all the analytic data to the users and any other medical professionals.
So, what I'm going to be handling mainly in the project is the subsystem design and implementation of the mobile application and the web server. So, we're going to make the mobile app using Flutter, which is an application that allows me to create an Android app and iOS app simultaneously. But if there are errors that we run into, I might just use Xcode and just make an iOS app since most of my group consists of iPhone users. We're going to be displaying the real time brain data and seizure alerts within the application so that the user who has the application with them can see all the data that we're collecting and see the alerts. They can also, within the app, select who their data is going to be sent to, like their healthcare professional or maybe their friends or family. We're going to use Firebase to help with logging in and having secure access so that only like the specific user can access their own specific data and now not allow for other people to access their data without consent, obviously. I'm also gonna work on making an Apache web server within the FPGA to handle with the data that we're collecting from our medical IoT device, and also make it so that it communicates with a mobile application correctly. Uh, and I'm also gonna make it so that the web server can handle API requests coming from the app.
In this slide, we will be going over the subsystem design and implementation of the EEG acquisition and transmission. The way this will be done is that a ESP32 will be programmed to collect EEG signals, which are the alpha, beta, delta, gamma, and theta signals, and will be sent to an analog to digital converter, which will be the ADS 1299. The reason for this is that the signals coming from the sensors are in analog signals, and they have to be converted to digital signals to be processed through our system. This system will handle any errors from the data, checking the packet integrity of the whole signal itself before it reaches the FPGA server. This will implement real-time transmission over Wi-Fi to the FPGA server. The ESP32 will also include any calibration support and serial logins for validation. The way this will be done is via Bluetooth or Wi-Fi capabilities of the ESP32. The ESP32 uses Bluetooth to configure Wi-Fi credentials via the mobile app. For any validation, it will be done through Bluetooth before it fully connects to the Wi-Fi. And that is the basic system that we have for the implementation of the acquisition and transmission from the wearable device to the FPGA server.
Hello, I'm Adrian Suarez, and I'll be taking over the subsystem design and implementation of the EEG headset and hardware. Basically, I'll be in charge of designing and building the wearable EEG headset and housing. Basically, the sensors that we are going to purchase will be put into this headset that the user will be wearing, which will be designed using a 3D printer. As well as I'll be taking care of the 3D printed chassis integrates the EEG sensors like we discussed. I'll be making a place to store the ESP32 and the battery as well. And I believe the ADS 1299 as well. I have to make a wearable for it as well. I will also be doing a lot of cable management, ensuring clean signal passageways and the user comfort, making sure that cables are not in the way, making sure steady connections with using between the sensors, the ESP32 and the ADS 1299. I will be also doing all the power management for the circuit, making sure it's safe for the user and the conditions that it's in, making sure it's not going to overheat, burn the user, anything like that. I'll be also focusing on the real world durability and the compact of the wearable, making sure that the user is not going to be able to break it just by sitting on a chair or just any day-to-day wear, making sure that it's very stable for everyday wear. As well as going back to the 3D printing of the headset, we'll be also using uh, the files from the company itself to be creating this headset housing using SolidWorks, as well as using SolidWorks. I'll also be using it to create the housing for the ESP32 as well as the ADS 1299 for the user, as well as designing whether we're going to use a backpack or implement it on the headset. That'll be determined later on.
This final slide is just to show all the references that we used for the proposal, and the final link that's in the bottom was a reference to this website that we used to help us in designing the template for this project presentation.